Right, hello, thank you. So I'm Tausif Rahman. I know just about all of you, so it's nice. So the talk I will give you is about parallel symbiotic random number generation for training Tsetlin machines on FPGA. It's a big title, but I think you can get the gist of what I will say to you just from the two pictures on the right-hand side. So the first picture at the top, this is a Halton sequence. It is a way of generating points randomly spaced with uniform density in a 2D space. And then this second picture, this GIF or GIF, this is how the sequence is applied in a Monte Carlo simulation. And this simulation is estimating the value of pi. So basically, this talk is about you generate random numbers and you apply it to an application. And in this case, the application is training Tsetlin machines on FPGA. So firstly, a big picture on why you would want to do any of this. Over the past 3 or 4 months, Gang and I have been working on something that looks like this, where you have a TM training accelerator with a processor and some dedicated hardware for training a Tsetlin machine. This is a big system level problem, and there's lots of complex ideas here. Our talk is about something a little bit more contained within this system. Why you would want to do this? Well, because you can get the parallelism of the Tsetlin machine in the hardware. You can get high throughput from FPGAs. And in order to do any of this, you have to think about how to use the resources that you have efficiently. So one of the tasks we will look at is how to generate random numbers for training the accelerator. Okay, so then we can discuss a little bit about the structure of the talk. Because the title is a little complex. So first we discuss why use FPGAs for training Tsetlin machines, where we will discuss the advantages of the TM, what is an FPGA. It will allow us to get some metrics that might be useful for deciding how effective our work is. This will allow us to get some challenges and requirements, and from those we can figure out how to generate random numbers for TMs. And to do that, we will look at existing approaches, some hardware requirements, some TM requirements, and then we can refine the requirements a little bit to get more clear metrics for what we want. And from all of that, at the end, I will present the contributions from this talk. This video is a TM being trained. If hopefully it will play. Okay, but hopefully it will play. It is a video of a TM being trained, and I have separated the TM into different components, which are either arithmetic memory or non-arithmetic parts. It's not playing.
Are you using the catalyst network?
Yes.
Use the Nikos bus.
Let me see. Let me just quickly check.
Catalyst is unstable.
Actually, I'm on the edgy room. Okay, let me check if this one. Okay. We'll come back to it. I can show you at the end. But the idea here is that I've separated the TM into its main components. I guess not. Okay. So some parts are for storage. Yes. Okay. So you see inputs come in the yellow, and then we have the memory elements at the top, which are the automata. And the main components here we have separated as memory components, which are the TA storage and the input storage. We have the arithmetic components, which are the clause compute. Non-arithmetic components, which are the clause compute, and arithmetic components, which is the class sum and argmax. And also we have classed random number generation into this as well. So these are the basics of TM requirements. Please remember these things on the side here. We will revisit this one. Okay. Next, FPGA, what is one of these? Typically, you can get them in a development board that looks like this. And inside it, there is a chip, which we call a system on chip. With reference to FPGA, that refers to something like this, where we have a processor and some programmable logic. So the programmable logic, if you take a look inside what is there, you see we have these configurable logic blocks, which are connected together. And inside those, we have these slices, which contain lookup tables, where you basically have some inputs some Boolean inputs going out to some sort of outputs based on how the table is configured. We also have other resources like digital programming, digital signal processing slices that look a little bit like this, where you have multipliers, shifting, some sort of ALU operations as well. And finally, we have memory components, which is the block RAM. So now we can take the things that I showed you before and start putting them onto the FPGA. So the storage, we use the BRAM for TA storage, input storage. For the LUTs, the logic slices, we put everything else. And then we can think about system integration with the processor. So you can see that slowly I'm using up all the resources of the FPGA. What is left is the DSP slice, and we think maybe this is a good candidate for the random numbers. Okay. So now we can look at a little bit about training requirements. So ultimately, everything is determined on the size of the BRAM, because that tells us how big the model can be and its model accuracy. But also, when we take data out of the BRAM, that has a latency as well. And ultimately, all of this depends on how energy efficient the model will be. So now we can say something about the FPGA requirements. So we want to not use the BRAM for random numbers. We want to use the LUTs frugally. We want to be fast, and we want to be parallel. Okay, so now some existing approaches. The most common one is the LFSR, which you see here, where the input is a function of the previous state. And usually it's called linear because the operations are linear. In here, it's typically XORs. They don't map well to the DSPs because you see there's multiple shifts happening, and we only have one shift block here. So it would have to be time. You would spend more clock cycles shifting if you wanted to use one of these blocks. Another method is these digital clock managers that the FPGA has, where you can dynamically change the phase of a clock at runtime. But unfortunately, there's only 4 of these on Xilinx FPGAs. So here you're hardware limited. And finally, this is something that I think Sven explored a little bit, where you can generate the random numbers off chip or on the processor and then just transfer them to the FPGA. But here you're bandwidth limited. So now we can discuss some refined metrics for what we want. We need random numbers almost every clock cycle. And secondly, we want to make pseudo-random numbers because when we started training the TM in the hardware, it became very difficult to debug. So you need a clear sequence so you know you can keep track of things. So that's why it has to be pseudo-random. Okay, now we can discuss the proposed approach. So the first thing I will discuss is the XOR shift, which is sort of like a LFSR method where you see the inputs come in, and then we have these XOR operators. This comes from George Maisaglia, and what he said was, firstly, I will say something about the period. It has a fixed period dependent on the number of bits that you put in the XOR shift. So here, this is a 16-bit one, and here, this is 7 bits. What he noticed, though, was that if you took tuples, say n-dimensional tuples of the XOR shift, what you find is that they become evenly spaced when you plot them into an n-dimensional hyperplane, which is what's here. And basically, he suggested that linear operators like this are not so great for where you need high-quality randomness. So then another 2 approaches we can discuss. This is called mid-square. This was proposed by von Neumann, and the story goes he was at a conference and he thought of this, and by the end of the night, he also discovered all of the lackings of it, which is, for example, if you pick a poor quality seed to begin with, so you basically pick a seed, you square it, and then you keep squaring the middle bits as you go along. But if you pick a poor quality seed, usually you will end up with a number that just keeps repeating, and often that is 0. So then Whale came and suggested that if you add something to the end of it and then swap the bits, you can get a larger period. But the same effect happens. You still get a number that repeats after a while. And one more caveat with the Whale is that you notice you have the multiply and then you have the add, but the issue here is that, and then you have the swap. So for us, we need at least 2 DSP blocks to implement this algorithm, whereas for the mid-square, you can put this into just 1. And finally, now we can go to proposed system. This is what we made. So we have the XOR shift, And we have this cluster where inside it, we can have either whale generators like this, or we can have mid-square generators like this, where the whale is implemented with 2 DSP slices, as we discussed before, and the mid-square is implemented with 1. And so the idea is when the mid-square, spoilers. When the mid-square gets stuck, the XOR shift gives it a new seed. When the whale gets stuck, the XOR shift gives it a new seed. When the XOR shift reaches its period, one of the generators will give it a new seed to restart it. So it has a symbiotic relationship. This goes into a flow of how that works, but I mean, I won't go into detail with this. You can just read the paper. But the idea is the same. This is meant to show the symbiotic relationship between the 2 generators. Then we need we need a way of evaluating how good the random number quality is and how useful it is for training TMs. So we created this script where we put in these inputs and it gives us the simulation time for FPGA. We ran this hardware flow and we got some random numbers out of it from the implementation I showed you. And then we put it into this NIST standard, which we will see in the next slide. And it allows us to see the random number quality. Then we take those random numbers and we train coalesce TM with it. Okay. So now we can look at some results of that. So this is the NIST test. They provide a series of tests for deciding how good the quality of random numbers are in terms of repetitions, whether they form uniform distributions or not. And we have our implementations here, the mid-square and the whale from the system that I showed you earlier. And notice that the mid-square fails almost all of the tests, whereas the whale for 1 million bits fails only 1. And as we keep increasing the number of bits, we notice that the whale starts to pass all of the tests and the mid-square starts to fail all of them. Okay, so now this is the main slide basically of the talk. We took those numbers and we put them into the coalesced TM, and you notice that, so here is the whale, here is the mid-square. CRAND is a Tsetlin machine trained in software. The LFSR is just a standard LFSR without the arbiter for resetting. And then we have the red showing the training accuracies of the model and the blue showing the number of random numbers used. So notice that the whale performs the best in terms of accuracy. It has similar accuracy to the CRAND, and it also uses the fewest number of random numbers. The issue with this is the trade-off, is when you start looking at the hardware usage. So notice that the whale uses more LUTs than the LFSR, whereas the mid-square uses roughly the same, if not fewer, but also performs better. So what this is showing, it doesn't really matter how good the quality of the random number is for the TM. It is robust enough to perform well, even if you give it the mid-square. So ultimately, we have 2 things we can offer from this. You can use the mid-square to train the TM, and it will give you better performance than the LFSR with fewer LUTs. Or if you want to do something that is not TM related, well, you can use the whale test, which will pass all of the NIST requirements and use roughly the same number of LUTs and flip-flops as the LFSR, with the only caveat being you have to use the DSP slices. So that's it. Now we can, these are the contributions. We have implemented this high throughput pseudo-random number generator. We've mapped them to DSP slices, and we've produced something that passes these NIST tests. So if you have a cryptography application, you can use it for that. We have developed a test suite for testing the quality of the random numbers and also for determining performance on Tsetlin machines. And then the main work for why we did any of this is to put it into the big picture that I showed you earlier for training the TM in the first slide. That's it. I have a demo tomorrow surrounding some of this, so please come. Thank you.
Thank you. Okay, so question. Well, Tosif, you're talking about the whale. So whale, is it what you've done?
Okay. So we have implemented both. So if you notice within this cluster, we have either the mid-square or the whale. So we give you the choice of either.
Right, so there is the core, but then you implemented the whole system.
Yes.
So I think that it's fair to call it Tosif
I wouldn't put my
generator.
name. No. But
Or
sure.
Rahman generator rather than whale.
Well,
it seems to be new, yes. So the core is the whale algorithm, but
yes.
the way it is implemented
At a system level, right?
Yeah.
It's different. Sure.
Yeah, thanks.
Thank you.
The questions?
Just a fantastic presentation, very nice. Yeah, so it's not maybe so much a question, but what do you think? I mean, here you gave a very nice example of what we should follow if we have certain resource
Yes.
in our hands. So
Yes.
if FPGAs, they offer us something,
Yes.
and it's not just LUTs, but other resources that are, it's a bit like what NVIDIA is making, trillions of dollars now. They've got graphical GPUs and they put them for the machine learning. Now we've got DSPs and they're good for random number generation. So that's what do you feel that we could, how else? I mean, it was a great idea, I think, that to use the resource and not just roll back to logic like LFSRs if we've got something here. So
Sure.
that's a good philosophy, I would say.
Yes. Okay. Our whole point of this was that we will be limited in the LUT count. So I can tell you, we implemented a 200 clause co-LSTM, Dan and I, for training, and that used 48K LUTs in a FPGA that has 53K. Now, that is including the interconnect, the control unit, and debug. So the point is you have to be significantly lower than the full LUT cost because you have implementation to deal with for routing and things like this, and that will have a cost as well. You have to find other ways of using the fabric, whatever they give you. So, yes.
I mean, just it shows that if we have fabric already there,
yes.
So maybe we could sort of think about other things, not just random number generation, but other things about Tsetlin machine, what we can do to use and to squeeze maximum of what we can have from an FPGA chip of a particular configuration, isn't it? So,
yes, definitely.
So we might use things for CSAMs, we might use things for what Ollie said, that for multi-mode recognitions, something for Booleanization maybe.
Right.
Yeah, it's interesting lesson. Yeah.
Yes. Yeah, something for further work for sure. Yes.
Thank you.
Yeah. Any other questions? No? Exciting.
Okay.
Very good. Thanks so much.